Thank you for your patience, everyone. All right, without further ado, we will move along in our agenda. So I am going to turn things over to John Lansing, and Vince, who you just heard from, I think is going to do a quick introduction. So John, I'm going to turn for the presentation over to you. So you will control the screen, and Vince, you are good to go.
Can you see my screen right now?
Yeah. Give me 1 second. We should be.
Oh, okay. Okay. Open. Like to capture. Okay. And unfortunately, I have to turn something on because it's the first time on this particular computer. So give me 1 second here while I give my system preferences access.
Well, I'll kick it off while we're waiting here. Thanks, guys, for allowing us the opportunity here to present. You know, this paper here on using ultrasonics in extreme gas conditions. We're lucky that we have, you know, we've coined him the godfather of ultrasonic measurement. John spent some time on the pipeline many moons ago. I think he's worked with most of the manufacturers of ultrasonic meters, and spent a lot of time at the calibration labs, also doing a lot of work there. Yeah, so we're fortunate to have John here. We're going to keep it fairly educational here, I think, John, and we've got Brad Perrin and Brian Lewis with us also from Kiera, which will give us the flavor from, you know, from the field. You know, it's not just us telling you that these things are the way to go. It's the guys that are using these things that are gonna, you know, sort of, I guess, verify that. So I'll let you go with that there, John.
All right, can you see my screen?
We can.
Okay, very good. I'm not so familiar with GoToMeeting, so I just want to make sure I didn't make a mistake. So again, Vince, thanks for the introduction. And as he said, Brad and Brian will both pop in and out of the presentation as they have some additional information to talk about the site specifics. So today we're going to talk about extreme. Let me get my laser pointer going here. Laser pointer. We're going to talk about solving extreme gas measurement applications using ultrasonic meters. So a little introduction. Many clients believe that gas ultrasonic meters are not suited for some difficult gas measurement applications, and we'll talk about those on this presentation. For applications where liquids are present, often orifice meters are used. Difficult to measure conditions often occur in midstream refining companies because we don't have nice, clean, processed gas. These difficult gas application conditions include the following, and there are many others, but these are the ones we're going to cover today. Occasional liquids in the gas stream that can affect and will affect the accuracy of any meter for that matter. Liquids that also affect the meter's long-term accuracy. So we're going to talk a little bit about what happens if your ultrasonic meter gets subjected to liquids and answer the question, is there going to be an effect on the long-term performance of the meter? Regulator noise has been long known to be an issue with ultrasonic meters. We didn't know this in the 90s, but we found out about it. And so we'll talk a little bit about dealing with ultrasonic noise from regulators. Often limited space is not available upstream and downstream because of the location where the meter is going to be installed in the piping. So we'll be covering an application where we have very limited amount of space and show you some data that was collected at TransCanada Calibration Lab last year. H2S is always a potential issue. In the past, transducer failure was very common. We also have to deal with potentially venting gas if we're using orifice meters. So we'll talk a little bit about ultrasonic meters and their use today with H2S applications. So to start with, we're going to talk primarily initially about two-phase measurement. When I say two-phase measurement, I mean there's natural gas along with some liquids. Many clients believe that using ultrasonic meters in these applications is not a good idea because the liquids will cause the meter to stop working. Many believe the orifice meter thus is the best solution for these applications because they always get a differential. The question I'll show you a little bit is about the accuracy of the orifice meter relative to the ultrasonic meter. Some wet gas testing has been previously done with other brands of ultrasonic meters at the CC Nunn facility. And we're talking about two-phase. And when I say two-phase, I mean, of course, natural gas and hydrocarbon fluid. It's a fluid that they use up there that's not as volatile as NGLs. It's called XL D80, but not water. Most of the time in the wintertime, they don't run water through the multi-phase facility because of potential for freezing. Previous presentations, I've looked at the combination of hydrocarbon fluid with water and didn't really see any significant difference with an ultrasonic meter. So we focus primarily now on just using hydrocarbon fluid and natural gas. Test protocol was established. What I'm going to show you was established by a client. He had applications in the field where NGLs were present on a regular basis. So he established a test protocol, which I followed, and I'll show you the results of that in a couple of slides. Previously, no testing had been performed on this 6-path meter that we're going to show you today. So there was no information about how it would perform under these same conditions. So to answer the question on how well does this meter perform with liquids, testing was conducted in January last year at the CC Nunn wet gas test facility just outside of Denver, Colorado. So for those that aren't familiar with this particular design, this is a 6-path crossing path design. We've got 2 vertical planes and 3 horizontal slices going through the meter. So it's a crossing path design with, again, 3 slices of the cross-sectional profile. Here's the meter installed on a nice sunny day in Nunn, Colorado, where the temperature was about a -10 out. Thank God the wind wasn't blowing. For this installation, we used a CPA 50E, which has been very common over the years as a flow conditioner and was used in previous testing. So the hydrocarbon fluid, as I mentioned, is a fluid called XL D80. The reason it's used is because it closely replicates NGLs without the volatility of an NGL. The gas flow rate measurement at the facility is done with a turbometer upstream of the meter under test, so it's under dry conditions with no liquids. Liquids are injected into the loop after the turbometer using a Coriolis meter for mass measurement. Reciprocating compressors move the gas in a closed loop circuit. It's an electrically driven compressor system. They do have a 3-phase separator to separate the water, the hydrocarbon fluid, and the natural gas. So this system can run basically pretty much all day. They use a heat exchanger to maintain stable temperatures to help reduce the uncertainty as we're putting a lot of energy into this recirculation system with the compressors. Ultrasonic meters in North America typically use a flow conditioner. So to replicate the previous testing the clients have done, we used a 10D, a 50E, and a 10D, along with the ultrasonic meter, and then of course the traditional 5D downstream. This is standard piping, and it's been very common in the industry, and we'll talk about some short coupled piping toward the end. But all this testing was done with the traditional 10D, 50E, 10D piping. Test pressures primarily were at 5,500 kPa, but the client wanted to do some testing at lower pressures. So we did a limited amount of testing at 1,100 kPa. The data today we'll talk about is emphasis on the 5,500 kPa range. 3 gas velocities were used in the 8-inch loop, 6, 12, and the max capacity of the facility on the 8-inch is about 15.5 meters per second. Clients identified the maximum liquid loading about 1%. In the multi-phase world, people like to talk about liquid volume fraction and gas volume fraction. So a liquid volume fraction of 0.01 is equal to 1%, or the same would be 0.99 for gas volume fraction. For those multi-phase folks in the wet gas world, this works out to be a Lockhart-Martinelli, which is kind of like the Reynolds number, if you will, of the wet gas world, of 0.41. The liquid loading was increased. The client wanted to find out, how much liquid can the meter handle before it will stop working on the lower pairs of transducers 5 and 6. So we did run some preliminary work up to a liquid loading of about 7% by volume, which would be a Lockhart-Martinelli of about a 0.32. So the primary protocol was to look at some minor light liquid loading. So we started off with 100% gas volume fraction and worked down to the 0.99, which is the 1%. but we can see some very small light liquid loading. They wanted to see, what the performance would be and what the diagnostics would say. So here's only a 0.1% liquid loading at this point. So we had some very, very small liquid loadings, and then we started jumping in 0.1 and 0.2% increments all the way down to the 1% by volume liquid. The gas volume fraction of 0.99 equates to about 7,500 pounds per million standard cubic feet of the XL D80. Obviously not pipeline quality gas. This meter was not calibrated prior to testing. It was baseline tested at TransCanada and shown to be within about 0.1% of the lab. And I'll show you data on that in a moment. The following graph was developed by Eric Harmon. He's the staff engineer at CC. The idea is to understand what is the meter's performance relative to an orifice meter. So what we have downstream of the ultrasonic meter was an 8-inch orifice meter. These orange circles were basically the performance on the y-axis in the form of error relative to liquid loading in the x-axis. So the red triangles here are the ultrasonic meter's performance relative to the orifice. We can see down at the bottom end here, they don't agree at 0, because the orifice meter obviously wasn't calibrated. The ultrasonic meter was within about 1/10 of TransCanada, but their upstream turbine meter was also not calibrated. It was not too important for them to have it calibrated. The most important thing is it's repeatable. So if we take a look at the 1% liquid loading, which was the previous client's primary interest, you can see that the graph on the meter is fairly linear up to about 1.5% liquid loading. At this point, the ultrasonic meter is over-registering around 4%. The orifice meter is doing about 9%. So to talk about liquids in terms of barrels per day, we're looking at about 3,800 barrels of fluid at this 1.5% liquid loading, or GPA. By GPA standards, I like to talk about gallons per 1,000 standard cubic feet. So we're looking at about 2 gallons per 1,000 standard cubic feet. As the liquid content increases even more, you'll see that the meter becomes a little more nonlinear, which is very common for ultrasonic meters. You'll also notice down here the orifice meter tends to under-register in the beginning. This is also not uncommon. Very traditional, very normal expected performance of both the orifice and the ultrasonic meter. So prior to testing at the CC Nunn facility, it was baseline, as I mentioned, at TransCanada. The baseline configuration was the same as we used at Nunn, Colorado at 10D, 50E, flow conditioner, and 10D. The purpose primarily was to determine and answer the question, will the meter shift after being subjected to liquids at 8,000 kPa? So 6 flow rates were tested for the baseline, roughly 30 meters a second, all the way down to 1.5 meters a second, essentially to cover the full range of the ultrasonic meter. Initially, the CC testing was done in January, or the TCC testing, prior to being sent to CC. After the testing on the wet gas, it was then retested in August of 2020. The same flow rates were used and the same flow conditioning and whatnot. So here's a photograph for those that haven't been to TransCanada. These are their reference meters upstream inside facility in Winnipeg. Here's the meter being tested with straight pipe upstream of the meter, downstream of this facility, this part of the facility here. Again, 10D with the CPA. So here are the results before and after. Wayne likes to calculate a thing called a flow weight mean error. So if we take a look at the January test data, the red line here is a flow weight mean error of about a 0.10 slow. This is essentially like a single meter factor that's discussed in OIML R137. Tells you how to calculate this. Kind of looks like a single meter factor for the entire flow rate range. The flow weight mean error on the retest was 0.08, essentially a difference of 0.02 between these two curves, which is what I would consider inside the reproducibility and the repeatability of both the meter and the facility. So now we'll talk a little bit about the Kiera Gold Creek facility, and Brian and Brad may step in and talk a little bit about some of the specifics here. I'm going to provide a quick overview. There are 2 meters were installed, a 4-inch and a 6-inch in April of 2021. Previously, there were no measurement on either of these 2 delivery lines. Facility changes in delivery required the addition of these 2 meters, so that was the intent of installing these 2. H2S levels can typically be around 2%, and an occasional glycol carryover will be going through the meter. Both meters have regulation upstream, which isn't ideal, but it is the way it is. One of them had around 200 kPa of differential, the other had about 1,000 kPa of differential upstream of the meter. Space was also limited for insufficient installation of a 10D CPA 50E in the 10D, so we'll be showing you what we use for that installation. Metering pressure typically around 7,400 kPa for both line sizes. In the photo you see here, the flow is from right to left. You can see we used a 3D spool here, CPA flow conditioner in 3D. So again, the flow is right to left of the downstream section on the 4-inch line. Here's kind of a view a little further back. So you can see the metering package here, as we call it in AGA and Measurement Canada. We have an isolation valve here in orange, and then of course the Fisher ET regulator upstream, which is taking roughly 200 kPa of differential for flow control. So the block valve in orange, again, is between the Fisher ET and the meter, typically 200 kPa with the metering pressure around 7,450 kPa. For those that are familiar with ultrasonic meters, the signal to noise is well in the strong range, 35 dB. If we get down around 15 to 20, like a lot of meters, that's where the meter might start rejecting waveforms. But the meter signal to noise is well in the solid range, no problem at all. The following profile graphs talk a little bit about what does the profile look like coming into the meter. So at the time of calibration on this meter, we can see the profile indication, symmetries on the y-axis and profile factors on the x-axis. The installation in the field in April looked like this, very similar symmetry and profile factor. After about 7 months, the profile factor is very close to the initial installed. So we've had liquids go through the meter during this period of time. The symmetry and the profile factor, once again, are very close to the initial startup condition, and they're also very close to the TransCanada situation. The other line size that was installed was a 6-inch meter. Here we could see the 3-inch piping. The 3D spool pieces are on the downstream side of the meter, and on the upstream side of the meter, we had to move the flow conditioner. So again, the flow direction is right to left. Here you can see the 10-inch piping was an eccentric reducer, flow conditioner installed here, and then the little less than 5D, a straight pipe with a thermal well and pressure tap upstream of the meter, and the spool pieces were just without a flow conditioner on the downstream. So we'll talk a little bit about why this installation was kind of reverse of what you might have expected. So again, the flow was right to left in the previous picture. The piping support in the middle required that the CPA be moved to the right-hand side. In other words, the piping support we see right here would have been right in the middle of the flanged area, so that was not going to work. So the client, with a limited amount of time, had to move the CPA and put the spools downstream for the 3D spools. The CPA now is around 5D on the upstream of the meter. Upstream of this meter, about 1,000 kPa of differential on a regulator, and again, this meter also runs around 7,450 kPa. Signal to noise, once again, well in the strong range, up above 35 dB signal to noise. So let's take a look at the flow graphs from this meter. What does the profile look like?
Hey, John?
Yes.
John?
Mm-hmm.
We did put the 55E on this meter install as well, right? So
yes, yeah. The 55E is located right here upstream of the approximately 5D spool piece. It's a little less than 5D. So it's right at the outlet, or right at the outlet of the eccentric reducer from 10 to 6, flow conditioner here, and then straight pipe into the meter.
Yep.
Okay. So here's the flow calibration profile at the TCC. You can see the symmetry and the profile factor are very normal, plus or minus a couple % on symmetry is not abnormal at all. Installed in the field in April, the profile changed a little bit because of the piping change and the eccentric reducer, primarily due to the eccentric reducer. After a few months of in-service, we can see the profile looks very similar to what it was at that time. So all well within the normal expectation of what you would expect in a field from upstream piping. So let's talk a little bit about the CPA and why it was moved. So Brian, do you want to add anything at this point, or do you want me to just kind of go through the slide presentation?
Sure, I can add a little bit. So when we did our model review and stuff, we had a very difficult application with piping spec for the facility and the design of the facility to supply this lift gas back to the producer was never in the original design for the facility, so it made it tough. As we walked through the design, we planned on installing, as mentioned before, in the normal position. But during our model review, we noticed we missed the structural steel. And so we went to install the meter. The flanges were resting on the structural steel support. So we contacted John and had a discussion with him and decided based on the previous testing that RMG had done, it should have no bearing on the meter. So we reversed it and installed it in and started up, and it worked really well with the atypical installation of this meter. The performance should have been fairly poor, and in turn with the design of the transducers and everything, it actually performed exceptionally well. The 55E plate made a huge difference, even with the shortened up run.
Yeah, and again, a lot of times these eccentric reducers are used to allow the liquids to flow through the meter, but in this case, it was used primarily to allow the meter to rest on the supports. So these eccentric reducers can cause distortion in the profile because you're allowing all the gas velocity to enter at the very bottom of the CPA flow conditioner, but the CPA 55E did an excellent job of getting the profile back to somewhat normal, even without any settling zone upstream of the flow conditioner. This is why the symmetry went from about a 1.23 up to about a 1.64. So a lot of folks would say, well, you know, what's going to happen when you have that kind of distortion at the meter? What about the performance of the meter? So due to the upstream eccentric reducer, again, the symmetry was somewhat distorted. So the question is, you know, what would be the effect on the accuracy of this meter? Well, obviously we didn't have time to take this meter out and recalibrate it and send it back to TCC. So I'm going to show you some data that was obtained by CPA back in June of last year. The intent of this collected data was to obtain Measurement Canada approval using a 3D 55E 3D package. Clients in Canada have been asking to shorten up the upstream piping for many applications, but as we know, this has to be approved by Measurement Canada or the installation would not meet their requirements. So a variety of tests were done. I'm going to show you just one here. CPA paid for all this testing. This one particular test sort of replicates the worst case scenario. Wayne likes to call this the D-boop, the double elbow out of plane, and then with the half moon plate in the middle creates a nasty distorted profile. So these are part of the tests that were required by Measurement Canada in order for them to obtain, them being CPA, to obtain approval to install an ultrasonic meter with the 3D 55 3D package. So CPA was required to provide a variety of tests. I'm just going to show you the worst case scenario test here that was done and give you a couple of pictures to show you what the piping looked like. So here we have a single upstream piping, 2 elbows out of plane. In the middle would go the half moon plate. You can see the half moon plate over here on the right hand side. This is the drawing right out of R137, the OML document. And for those that aren't familiar with the 55E, it looks like the 50E, but it's twice as thick and it has counterbored holes in the middle here to where their thickness is not the same. So let's take a look at the baseline condition. Now baseline means 100D of straight pipe, the CPA 55E installed at 3D upstream of the meter. Here is the double elbows out of plane with a half moon plate. We can see a very substantial shift. Now these graphs are all the same vertical axis, horizontal axis for this meter test, as well as the ones I show you for the 6-inch meter. So we can see the symmetry here is about a 1.15. This is about a 13% deviation from the, or 12% from the baseline testing. Both these graphs were taken at about 7 meters per second. This was at baseline at the lab, and this is baseline with the double elbow out of plane. The effect on accuracy was about a 0.08%. In other words, Wayne calculates the flow weight mean error on this based on the flow data, and it showed about a 0.08 for this profile versus this profile. So I think we can assume that the distorted profile we see at the Kiura site would likely create quite a bit less error. And again, we're talking under 0.1%, which is less than 1/3 of the maximum permissible error by TransCanada. The next to the last subject to talk about is dealing with control valve noise. We all know the control valve noise can interfere with an ultrasonic meter. Ideally, you'd want to install the control valve downstream of the ultrasonic meter, but in this case, that wasn't possible. So both of these cases, the regulator was installed upstream. Again, 1000 kPa differential on the 6-inch meter still had a very high signal to noise. Now the possibility, the reason why this is because of the much higher power that's provided to these transducers and the sealed titanium design of the transducer. So the concern about the regulator was discussed with Brad and Brian before the installation of this to assure them that the meter would continue working without a problem. And to do that, essentially what I'm going to show you is some data from a field installed meter in Europe where the regulator was installed upstream of the meter. So here we have a meter installation package. This is the ultrasonic meter running at about 310 kPa. About 4,000 kPa is immediately upstream of this regulator. You can see the regulators directly in line with the meter with just 2 flow conditioners in the middle to stabilize the profile. The gas temperature is typically -20 C and colder due to Joule-Thomson. This meter's been in operation for 6 years, 100% transducer performance, no failures. So I use this as a method to show the Kiura that this meter can handle the kind of differential that they're looking at. Kind of the last topic of discussion, and we'll turn it over to some questions, is the past ultrasonic transducers have been prone to failure with high H2S. The reason why is the electrical connectors and get attacked by the H2S and eventually would cause the transducer to fail. But today's titanium transducers are fully sealed, so there are no electrical connectors being subjected to the gas and the hydrocarbon, the H2S. So this means that with no transducers to fail, they're much more reliable than we had, say, 10 or 20 years ago. Thus, ultrasonic meters that are equipped with sealed titanium transducers, orifice meters are often used, but now we can utilize transducers from ultrasonic meters because they are much more reliable. Orifice meters also pose a hazard from potentially exposing the personnel to H2S during plate changes, and we all know orifice meters have a limited rangeability, so plate changes are inevitable, where an ultrasonic meter has got a much greater rangeability. Also of importance more and more these days is the venting of natural gas in the atmosphere, as well as the venting of H2S. So in conclusion, these 2 meters have been operational since April of 2021. The difficulties they had to overcome for flow measurement were fairly extreme. In this case, it would have been very difficult and much more expensive to use orifice meters in lieu of ultrasonic meters in this application. The difficulties Kiura had to overcome include the sour gas that we talked about, liquids occasionally coming through on the key carryover, close coupled installation due to the limited space, and of course the upstream regulator noise. The facility continues to balance month to month. There no failures have occurred of any kind. Occasional liquid carryover has occurred, but it has not affected the monthly balance, and the meters continue to operate accurately. I'll let Brian talk about some additional comments on the speed of sound as well as the ongoing performance monitoring.
Yep, so as part of our regular PMs and our measurement program to our producers, we do monthly checks on the speed of sound to verify meter performance. We have a multi platform of ultrasonic meters, and up in the Montney Basin we see a lot of contaminants in the gas, and with the different transducer design on the RMGs, the RMGs are not inside the flow path, they're recessed, And what we're finding is they don't get foul, they're dirty, and with the higher power, it seems to not affect them. So when we run our monthly checks on the SOS with our current gas composition, it's maintaining very steady and not a lot of changes or error percentage found. It's almost pretty much month after month bang on the money, which is great. So with this application, we had a lot of challenges to be able to measure this. We have, slugging flows, we have liquids present in the gas, we got a bit of glycol carryover. The flow rates can fluctuate from, 50 dec all the way up to 2,500. So a lot of different challenges, and where the piping spec is and regulators there, without doing a major redesign of the facility, it made it very difficult. So we'd reached out to Strata Controls and RMG to see what solutions were out there, and they went above and beyond for us. This project came on very quickly because of a producer's needs, and we were 5 weeks basically from start to finish to get the metering tubes, pressure and temperature transmitters, and the RMG meters to site, with doing the calibrations at TCC and doing all the QA QC checks. Each month we check the meter performance, and Strata Controls and RMG are there to support us. Their customer service has been phenomenal, and one of the big things that helped us make our decision, as being these meters were new to us at Kira, was the customer support, and also they gave us a try before you buy. So it helped reduce our risk quite a bit in making the decision to try out some new technology, and they've been phenomenal in the application. We put them in a situation where ultrasonic shouldn't work, wasn't our initial design preference. It just ended up that way, the way some of the things we missed during construction, but no effect on measurement and extremely accurate.
Okay, thank you, Brian. And a follow-up presentation will be performed hopefully at the May 29th Canadian School of Hydrocarbon Measurement. And in keeping with what Justin had to say, I might propose we move the conference to just someplace in Hawaii like this. So at this point in time, we'll open it up for any questions, and both Brian and Brad should be able to help out answer any questions about the facility that you may have.
Actually, John did get a question in. It's from my good friend Darren at Shell. Hi, John. Happy New Year. Do you have an indication of the USM performance at the 7% liquid load? You mentioned you tested at CC.
Yes. Yes, a good question. We ran the meter all the way up until the lower two pairs of transducers stopped working. As soon as we dropped the liquid content, they came back in. At that point, the meters, I've got the exact number in a spreadsheet, but both meters, the Orifice and the ultrasonic, were over-registering on the order of around 30 to 35% because of the liquid cross-sectional area causing the gas velocity to read high, and as a consequence, the ultrasonic over-registered, but it was very close to the Orifice meter at that point. Any other questions?
None that have come in so far. I have a question actually. With the recessed transducers, is there any issues with any either solids collections or anything in that small space in the pipe?
In one of my former careers, we did a test to show what happens when you have, we basically ran liquids through the meter and then injected bubbles. And what we saw was a cyclonic effect inside the port. When the transducers pull back slightly, the face of the transducer tends to stay cleaner, and you can get some buildup in the backside of way in the very back of the transducer port, but this doesn't have any effect on the transducer's operation. So there's pros and cons to having transducers protrude a little bit versus having them pulled back into the port. The big plus in pulling back in the port, what we learned many years ago, was the face of the transducer tends to stay a lot cleaner due to this kind of the cyclonic effect of the gas and the fluid coming by the port.
Sounds good. John, I am more than happy to take on the suggestion. I can pass on to Mike, and I think if RMG is willing to, be a primary sponsor of that location, I'm sure we'd all be more than willing to move. So you can go talk to the bosses. I'm sure they'll be absolutely open to that.
All right. Well, we certainly should step up to the plate. So.
Right. I don't see any other questions, John. So thanks very much for the
Okay.
presentation.
Thank you.
Thanks.
I guess you'll
Thanks,
take
Kiara,
control now, right? Mm-hmm.
Yeah, and thanks, Kiara. Thanks guys for coming on. Brian, appreciate your time. Brad, appreciate your time. If anyone has any questions about the presentation, John, is this? Can you make this presentation? Actually, you know what? Why don't we just say we'll wait until after the hydrocarbon school, and it'll be posted after that. So I won't bother to ask you for a copy of this. We'll wait till after the school itself. So.
We're more than likely to add a couple more slides of some additional information. We've got 2 more months, so but for sure it'll be available. That's
great. Thanks very much. And
You're
just
welcome.
one more plug for the school as well. If you did want to see this presentation again, or you missed something on it, obviously we are recording. We will eventually get all of our recordings from our meetings onto the website. But make sure that you register for the school as soon as it's available. Again, I think that all signs indicate that it will be a go